We're going to now give a polynomial time algorithm for finding a largest, meaning in terms of cardinality. We're not yet talking about matching. That will be the topic of future lectures. A largest common independent set. In other words, we want to find I in I1 intersection I2, where I1 and I2 are independent systems of matroids on a common ground set, of maximum size, meaning maximum cardinality. And I want to mention a few things about what we mean by polynomial time algorithm. So in particular for this problem, we're not assuming that we're writing out all of I1 and I2. So one thing, this is the first time we're talking about a polynomial time algorithm for this kind of problem. And the question is polynomial in what? And it's certainly not polynomial in the cardinality of calligraphic I1 or I2. So the note I want to make is that the matroids M1 and M2, same ground set, are specified via an oracle to test membership in each of I1 and I2 respectively. So for example, if you're thinking about just a maximum weight independent set in a single matroid, we showed that the greedy algorithm achieves this, and you can run the greedy algorithm by order E calls to this membership oracle. So it's polynomial with respect to the number of calls to the oracle. And the way we're going to apply this is that for any new matroid, we just need to make sure that indeed even if it has, well, most matroids of interest are going to have an exponential number of independent sets. We just need to be able to check, given any subset of E, the ground set, whether or not it is independent. And we've already seen the only algorithm we've given, the greedy algorithm, we can run with a small number of calls. So in other words, I1 need not be enumerated. Kind of an obvious point, I guess. So we want to find the maximum in the number of calls to the oracle. Max cardinality of I efficiently in the cardinality of E, and using the oracle as a unit of our computation. Okay, we spent time when we were talking about matroids developing machinery of a directed graph. We're going to do something similar, but now for the matroid intersection problem. And things are a little bit more complicated, but we should use the results of those lectures as intuition to help us understand what's going on. So again, for MI are two matroids, and for some common independent set, I element of I1, intersection I1 and I2, define a directed graph, which I'm going to denote in similarly to to our notation from last time, but now keeping track of both matroids. Again, if it's clear that I'm talking about matroids M1 and M2, perhaps I will drop the subscripts, but I don't want to confuse it with a situation where we're talking about the directed graph just for one matroid. On a vertex set, the vertex set, as before, is going to be the ground set and a set of arcs. And let me write a of I as we used in our previous notation. So we have a similar picture. Here is I, and here are all the elements in E that are not in I. But now the direction when we were talking about the directed bipartite graph for a single matroid, we only had edges from I pointing towards the complement. Now we have edges pointing in the reverse, and that's because we have two matroids. So for any y here on the left and any z on the right, yz, let me call this z1 and let's call this z2 just so we don't have edges on top of each other. So yz1, meaning it's an edge pointing from y to z1, this arc exists if and only if I minus y plus z1 lands me in an independent set for the first matroid, but possibly not the second. And the reverse arrow indicates that this relationship holds for the second matroid. So in other words, z2y is in A if and only if I minus y plus z2 lands me in an independent set. So again, whenever you have an edge, regardless of directionality, it means that I'm taking away y, that's already in the independent set, and adding the other endpoint. And the directionality is really just a label that is telling me, am I guaranteed to be in the independent set for Matroid 1 or Matroid 2? Okay, so this is what this means. Don't be tempted to think that an arrow from z2 to y means that I am taking away z2 and adding y. That's what we had just for the previous case. An edge means I'm taking away whatever node is the left endpoint and adding whatever node is the right endpoint. And the directionality is just telling me, am I independent in, it's just a convention that we'll see will be useful in a moment. But that's telling me, am I independent in, with respect to Matroid 1 or Matroid 2. We're going to use this graph now to come up with an augmenting algorithm. So, again, given our two independent sets, our independent systems, and given something in the intersection, I want to either assert that this is the largest possible cardinality set in the intersection, the largest common independent set, or I want to find a way to augment it. So let's define x1 to be the set of nodes that are in E but not in I. In other words, the set of nodes here on the right, such that let me write this as a z here, just to be consistent with what we've seen so far, such that I plus z is an element of I1, and x2 is defined similarly with respect to the second matroid. So again, it's every z on the right where I could add that to I, and end up with an independent set of I2. Clearly, if x1 and x2 have some intersection, I just add that to I. That's the easiest thing. I should scan through the right-hand side and check whether or not x1 and x2 have intersection. And if they do, I should immediately add it. So in all of the pictures that I'm going to draw x1 and x2 without intersection because it's immediate that we could add. So what is our picture? Here again, here is I, and here I have everything that is not in I, but now I have some differentiation. Some things are in x1, and some things are in x2, and some things are in neither. Okay, this is these 2 points in the middle are in neither. If you add those to I, you are not independent. You're not in I1 or I2. And then there's a bunch of edges here. I look at this directed graph. So we have a bunch of edges. So the first case that we're going to consider is the setting where there is a path that starts in x1 and ends in x2. So to draw the picture, perhaps it starts at some z0, follows an edge. Obviously, that edge has to be pointing from the right to the left, and we'll have to keep in mind what the directionality of the edges mean. Ends in y1. Then perhaps there's an edge that ends in z1. Note that z1 is in neither x1 nor x2. There's another edge that goes back to some other node y2 in I. And then finally, we follow this and we end up in z2, which belongs to x2. So case 1 is that d m1, m2 of I has a path from x1 to x2. If x1 and x2 again have an intersection, then that path has just one single node. It would have one single node, so it would have a length 0. I'm not going to draw that, but that's possible, and it doesn't contradict. This statement. And the statement that we're going to prove is that if there is such a graph, if there's such a path, then we can augment I to a common independent set of size at least one larger. So let's let P be such a path of shortest length. In other words, be a shortest such path. The claim is that if I look at the new set, I dash, which is the symmetric difference between I and the vertices of P, that's what VP means, I dash is an element of I1 intersect I2. So in this picture, that would mean that the claim says that if I look at I and I subtract y1 and I subtract y2 and I add z0 and z1 and z2, that's a symmetric difference, then this is in I1 intersect I2. And indeed, you can see I subtracted 2 things, I added 3 things, so I have augmented. All right, let's see how this works. So I'll write this as a theorem that indeed this I dash, which is equal to I and the symmetric difference of I and this path, is an element of I1 intersect I2. We're going to rely on the results from the Matroid lecture 7 that talked about unique matchings in these directed graphs. That's the machinery that we're going to be using. And the fact that P is the shortest path is going to allow me to use that machinery. So note that because P is the shortest x1, x2 path, the arcs in P leaving I form the only, in other words, it's unique, that was the key in those lecture 7 results, matching in the graph dm1 of I. Remember that dm1 only has edges from the left to the right, and an edge specifies when a particular swap maintains independence in the matroid. So they specify a unique matching, the only matching on the nodes VP minus Z0. I'm going to call this star star to refer back to it. But let's look at a picture to understand what that's saying. So let's look back at this picture. So what this is saying is that the arcs that are in P, so P has five arcs, 4 arcs, 1, 2, 3, 4 arcs, and five nodes. It's saying that the arcs leaving, that would be this arc and this arc, the arcs leaving, have to form a unique matching among nodes y1, z1, y2, z2. We specifically exclude z0. Obviously, there can't be a matching on an odd number. And the argument is that it's unique, because if it weren't unique, if there were another matching, say y1 also, there were an edge from y1 to z2 and y2, remember the arrows are important, and y2 to z1, then there would be a shortest path. And in this example, we can see it. There would be a shortest path because I'd be able to go from z0 to y1 directly to z2. So I would have a path of length 2 instead of a path of length 4. So that's how the shortest path gets its uniqueness. Now also, for any z that's on the right-hand side of this path, in other words, it's on the vertices of the path, but not in I. That means it has to be on the right, and also excluding where it starts. Note that I plus z cannot be an element of I1. Because if that were the case, then that means that the element on the right would already be in x1. Remember that if I plus z is in I1, then z has to be in x1. And what this is saying is that of all of these nodes here on the right, only the first one can be in x1. Because if z1 were in x1, then I could have just started my path from z1 and had a shorter path. And so I know that I know that this is the case. So let's so else there would be a shortest path. Let's call this the second star. Now let's let J be the set that's equal to I, symmetric difference with the nodes on the path, but again without z naught. And so in the picture on the previous slide, this means that J is equal to I minus y1 minus y2 plus z1 plus z2. So in this case, you see that for this J, we have that the cardinality of I and J is the same. What else do we have? Also, my claim is that with respect to the first matroid, the rank of I and J is equal to the rank of I. In other words, just the cardinality of I. And why is this? This follows from the property star. Since z1 and z2 have to be in the span of I. You see, if it's not the case, if any element of J were outside of the span of I, then it would mean that I plus that particular element would still be independent, which we've ruled out. And therefore, whatever is in J, but not in I, namely z1 and z2 in our example, they have to be in the span of I. Now we're going to use the property star star, and that's just saying that there's a unique matching. So from star star, we know that there exists a unique matching in dm1 of I in this directed graph on the symmetric difference between I and j. And now finally, we have satisfied all of the assumptions of the second corollary in the Matroid lecture 7, lecture on part 7 of the Matroid lectures. So by the second, it's the last corollary in the lecture on Matroids part 7, we know that because I plus Z0 is an I1, that's just because Z0 is an X1. It's by assumption. This implies that J plus Z0 is an I1. So what did we show? We showed that this is in I1, and just by symmetry of this argument, we show that it's in I2. In the next lecture, we're going to consider the second case. What happens if there is not a path from x1 to x2? And we're going to show that in that situation, it must be that we already have an optimal, a largest cardinality set I. So we'll pick it up in the next lecture.